right, now we're going to transition into our, not lightning, but rapid fire talks. First up is Bora Benjamin from the University of Washington in Seattle.
So hi everybody, can you hear me? Yeah, okay. So I'm here today to talk about challenges for optimal control of contact-rich dynamics. I'm from UW, and this work has been done in conjunction with my advisor, Professor Sam Burton, the session chair. So this work largely draws from our archive preprint. This link will be posted on the last slide, so if you're interested, please write down and come chat. This work has largely been motivated by the just success in these two fields. The first is reinforcement learning, which has just really taken off lately. It's becoming an increasingly popular avenue for optimal control, and there have been many recent results for simulated systems. The second really hot field has been robotics in general. There's been a lot of new hardware development, and these robots have been increasingly capable. But there are going to be some challenges when bringing these two fields together. And the focus of this talk is one challenge that we have identified. And I think a system the simplest mechanical system that exhibits the specific pathology is the box. And the box has these, exhibits these pathologies due to its contact dynamics. So for the rest of this talk, we're going to deal with a box that's dropped from some vertical height for some fixed time horizon. And when we talk about theta, that's the rotation along the axis coming out of the plane. The box's impacts are purely plastic, so that means if you're going to drop a ball and its impact with the floor is plastic, that means it just stops, and the contacts are frictionless. So you can see here there are two boxes being dropped and rocking. And so an interesting thing happens when you do this. You get discontinuous trajectory outcomes. So you can see there's three branches, one with a positive initial orientation, so that's on the x-axis, and then it ends up with a negative final orientation. There's one where if you drop the box with no or zero angular orientation, it just stays that way. And there's also the other case. And this really just illustrates the discontinuities can arise from impact dynamics. Now we're going to introduce a maneuver. We allow ourselves to actuate along the angle of rotation, and we associate a cost function. So we quadratically penalize or deviations from our desired angle, but we also penalize control input. And so this allows us to specify a 1D optimization problem. So even though it's not convex, we're reasonably confident that we can find solutions. And when we optimize over this, we get discontinuous trajectory outcomes. So again, on the x-axis, we have initial rotational orientation. On the y-axis, we have final rotational orientation. The colors indicate the final mode. So blue indicates right contact from the perspective of a box. Red indicates left. And we're shooting for a final angular orientation of 0.01. So as you can see here, it's discontinuous. And this propagates when composed with a cost function. So here we can see a 3D landscape. But if we fix theta and we move along a single control input, we see that, again, it's discontinuous. And this is basically the theme of our paper, that if you have a discontinuous trajectory outcome, it'll propagate all the way through to your value functions and optimal policy. So again, you see here in the case of the value function. And this is finally reflected in the optimal policy. So some important takeaways from this is that recently in reinforcement learning, it's been very popular to apply policy gradient methods in hopes of converging towards an optimal policy. But if you're trying to optimize towards a discontinuous optimal policy, you're going to have a challenge finding it. And so that's why basically we need to find ways to optimize policies for discontinuous trajectory outcomes. If you have any questions, please go ahead.
Okay, great. We've got about just under a minute for questions. Yeah, let's thank Bora.
Yeah.
We've got just under a minute for questions while Robin comes up.
Yes. Can you give us a sense of which way these discontinuities can go? Where does the box bounce? Does it roll?
So the discontinuities come from the possibility to go through multiple context sequences at once. So that means in the case of the box can either hit the ground straight down, it can hit right and then rock, or hit left and rock. And that's where we get these different branches. So if you were to drop over a longer period of time or from a greater height, I kind of picked this case to kind of minimize the discontinuities. You can actually just start experiencing them more and more as it rocks further and further. So yeah. So only for rigid systems, plastic impacts.
Okay, great. I think we're going to have to take the rest of the questions offline.
Yeah. Got it.
Perfect.
Yeah.